Welcome to this presentation. My name is Sjoerd Boersma. I work at the SuperGrid-Institute in France, and the title of this presentation is Enhanced Power System Damping Estimation via Optimal Probing Signal Design. First, I would like to start with a few notes on SuperGrid-Institute. This is the Research and Innovation Center in France where I'm working. The main objective of the SuperGrid-Institute is to do research on the transportation of large quantities of energy from renewable sources to the grid through HVDC links. So, for example, a large wind farm is situated in the sea, at sea, and the idea is that power is generated there, and you want to transport these large quantities of power over sea to the mainland via HVDC links. So we develop techniques to do that, and we do research on this. Furthermore, one point is the strong collaboration that we have with industry, and I would like to invite you to check our website for interesting job offers. Here is our website. Then also a note on the project collaborators. First, Xavier Bombois, he's working at the CNRS in France, Research Institute. Second, Luigi Vanfretti, working at the Rensselaer Polytechnic Institute, RPI in the USA. And also Vedran Peric, working at the Technical University of Munich in Germany. And internally we worked on this project together with Juan Carlos, Roman and Abdelkrim. These are all from the SuperGrid-Institute. So what I said before, we have a strong collaboration with industry, but at the same time we also have a strong collaboration with scientists. Then the problem statement. What problem did we work on in this project? Okay, so here we have on the y-axis we have a power measurement, and on the x-axis we have the time. So here you see a true measurement of a system taken from a power system in the United States. And well, you have some small oscillations, and around 400 seconds there is a line that tripped. So this caused a little bit more oscillations, okay? And when you see here again at around 225 seconds, a second line tripped, which actually causes here these very large oscillations, and the result was a blackout. So again, this is a measurement from a true system. So of course, undesired costs a lot of money. So post-analysis showed that actually here, after the tripping of the first line, the damping was around, or just before the tripping of the first line, the damping was around 7%, which is okay. So this is green. Then also we saw that after the first line tripping, they saw that the damping decreased from 7 to around 3.5%. And further in time, you see here the damping became 1.2%. So it should be clear that if you have a low damping, then you can have large oscillations in your system. So the idea, of course, is that you want to detect if the damping becomes below a certain threshold, such that you can act, okay? But in this case, there is post-analysis showed that indeed the damping coefficient decreased as time increased, and here again the system became unstable. Now the idea of the work is that to do damping monitoring, so to actually monitor this value, this 7%, 3.5 and 1.2%. That's one of the objectives. You want to monitor that such that if it becomes below a certain threshold, you have to act, and all in order to prevent that this occurs. That's the idea. Damping monitoring. Okay, then the proposed framework. How do we think that we can do it? We want to do it via system identification. So first of all, you have an experiment for system identification on the network, on the power system that we want to analyze. So therefore we excite it with an excitation signal. This is U of t. We call this a probing signal. This can, for example, be active power. Okay. Then from the network we take a measurement, which is Y of t. This is a consequence of our excitation, of our probing. And this measurement, Y of t, can, for example, be phase angle difference. Then both the Y of t and U of t measurement and probing signal go into the system identification box in the algorithm, which gives us a G hat, which is a mathematical model that characterizes the dominant characteristics of the true network. And from this G hat we can evaluate the damping coefficient zeta hat. Yeah, we can get zeta hat, so this is the damping that we are after, and the corresponding frequency. Okay, that's the main idea. So we do an experiment for identification. This gives us information on the system. This is what we are going to use in our identification procedure, which gives us a model G hat from which we can evaluate or estimate the damping coefficient. Now the question that we asked, can we ensure a quality measure of this estimation? Okay, that's the question that we asked. Because maybe we have an estimation, but is it a good estimation? So for this, okay, we found a way to do that. I want to discuss then what a quality measure is. So in this figure you see on the y-axis you see accuracy, and on the x-axis you see precision. Here in the non-accurate and non-precise you see here the red crosses which indicate an estimation of this true value. Here you see that the estimations are relatively widespread and not very close to the true value, so not accurate, not precise. Then here you are more accurate but not very precise, so they are relatively far from each other, but they are more closer to the true value. Then also here you see more precise, less accurate, so they are close to each other, but they have a bias, so they are relatively far away from the true value. And then we also have here precise and accurate. Something that of course we would like to have is that we are close to and the true value, and all the estimations are close to each other. So these are quality measures of an estimation, and the proposed method discussed in this work is focused on this area. So it's focused on precision of our estimation. In fact, what we tried to do, because here I come, we wanted to have this estimation, but we wanted to ensure precision. In fact, we try to, or actually we do that, we ensure an upper bound on the variance of this estimation by choosing a probing signal. So we find an optimized probing signal that actually ensures an upper bound on the variance of this estimation. And that's what this work is about. That's what we do. So then, okay, I said that the probing signal U of t can be active power, for example, injected at the bus. But we also have it more precise. We focus actually on the multisine parameterization of this probing signal. Here you see one example. Here you see the U of t. This is our multisine, where we have a frequency and a phase component. For this one we choose a grid, okay, and for this one we choose it random. But what we actually do is we find an optimized amplitude of the multisines. For example, this is an example. Here you have AI, and here you have the frequency in hertz, so from 0.1 to 5 hertz, for example. This is our probing signal. You see that the amplitudes are everywhere 0.1. And the question is, this is the question, does this ensure a certain variance on our estimation? That's the question. This is the time domain realization. Or maybe it is this realization, this probing signal, that ensures a certain variance on our damping estimation. So here you see that certain elements, AI, certain amplitudes are 0 or very low. So this is the question. So the framework that we have proposed in the paper, we are going to find actually these AIs that ensure an upper bound on the variance of this damping estimation. So these are the ones that we find. Now, it is not so very difficult to imagine that in order to find this optimized probing signal, we have to have some information on the system. We have to have some information on the network, okay? So therefore it makes sense that we need to have an initial G hat. We need to have an initial model, and this model can be used to actually find this optimized probing signal. okay? And we do this via an initial base experiment. I will come back when I show the results. I will come back to how we do that exactly. But for now, I just want to say we have a G hat, a base G hat goes into our optimal probing design method. So this is what we have proposed in the paper, which gives us for the second part of the experiment an optimized probing signal that ensures this upper bound on the variance. Now, one slide with math, I want to show just what we have done. This is our optimization formulation, optimization problem. Here you see a minimization of two terms, so the details are not so important. Here it is important that this is the decision variable, so this is what we actually find. This is our AI, these are the amplitudes of our multisine. And here you see the constraints. This is actually the covariance matrix of our parameters, and this includes here the damping coefficient. And here you see the actual upper bound. And this is what we are solving. So this is a very nice LMI. So therefore this is a very nice convex problem. Here you see also that there is a G hat involved. So indeed, what I said, we need a G hat. And the thing is important here is that we in the first term have the power of the probing signal that we try to minimize, and in the second term we have the power in the measurement that we want to minimize. And here you have C1 and C2. These are weights that we can use to make one term or the other more important. Okay. What is important here is to see that we are not only minimizing the probing signal, we want to excite less as possible, but here we also minimize the deviation of the network from its nominal value, from its operation value. And this is also very important. So we do not excite and the system is going to move everywhere. No, we try to minimize everything such that the upper bound is ensured. Okay, so that was it. So now we go to the simulation results. Here is the example that we have studied. Or one of the examples, we studied different ones. Here you see the Kundu network with the 4 generators, G1, G2, 4 and 3 and 4. However, we have also included here an HVDC link, as you can see here. And this is actually what we're going to use to excite or to probe the network. We are using the active power through the HVDC link to probe the network. And then we take a measurement y of t, which is actually the phase angle difference between these two buses. This all is programmed and simulated in DMOLA. So the true network is simulated in DMOLA. Then here are results with certain coefficients. These we see here an estimation. This is the minimum damping coefficient estimation with respect to the true minimum. Okay, so they are relatively close. These are the corresponding frequencies, also good. Here in the upper plot you see a measurement y of t. And in blue you see the measurement from the MOLA, and in red you see actually the output of the estimated model G hat. So here in the first 60 seconds you see this part is the base experiment. So here we get 1 G hat, which we're using in our optimization problem to get for the second part an optimized probing signal, which is this one. So here is a base probing signal, then we get an optimized probing signal, and here we can say that after this excitation we do again an estimation of our damping coefficient, that we can say that here we have an ensured variance on our damping estimation. So this is the optimized probing signal. And you can see with respect to the base, it has less power content, so which is good. So this is a little bit how it works. What we also have here is that here you see the base experiment amplitudes of the multisine, okay? And you have here the optimized one. So for the second part of the simulation, these are the red dots, okay? So you see that there is much less power in our optimized signal because there are less amplitudes bigger than 0. And also that here is the dominant inter-area mode. It's the most low damped inter-area mode that we actually excite around. Okay, so this is interesting. So We are trying to get this information that we need by just exciting an interesting point, instead of exciting everything. So this is what the optimization problem finds as well. So I want to invite you to look at more results. We have results on the IEEE 14 bus and on the Nordic 44. And of course, analysis and details can be found in the paper and also in a journal paper that we have submitted. But the preprint is available online. So I would like to invite you to look there for more details. So now I want to thank you for your attention. And if there are any questions, feel free to ask.